Hello, everyone. My name is Eric Massonet, and today we're going to have a conversation about information technology and climate change, including some key challenges and opportunities related to the cloud, big data, and artificial intelligence. Joining me in this discussion today are Rob Aitken of ARM, Samantha Alt of Intel, Nicola Peel-Moulter of VMware, Mo Tanabian of Microsoft, Ellie Ye of Applied Materials, and Cliff Young of Google. So welcome, everyone. So I think it's safe to say that there are very few aspects of modern life that haven't been touched by semiconductors. And more broadly, that digitalization has brought tremendous societal benefits over the last 50 years. There's also a general recognition that digitalization can play a key role in climate change mitigation. Some examples include renewable energy integration, smart buildings, advanced manufacturing processes, and dematerialization, just to name a few. But it's also known that digitalization brings with it some environmental challenges. For one, IT device manufacturing can be very energy and resource intensive. Cisco projects that by 2023, there will be nearly 30 billion devices connected in the world, which is a staggering number. A recent study estimated that the combined energy footprint of data centers, networks, and all of those connected devices account for about 6 to 7% of global electricity use. And that may rise as demand for data in these systems grows rapidly. For example, IDC projects that the amount of data created in the world is going to increase by more than fivefold by the year 2025. Furthermore, all of that IT equipment will eventually lead to millions and millions of tons of e-waste every year, and the UN estimates that those quantities will double by the end of the decade. And finally, when it comes to climate change, there are dual narratives that are at play among analysts regarding the future of digitalization. In one narrative, analysts predict unsustainable growth in IT's energy use and emissions due to the rise of 5G, the Internet of Things, and artificial intelligence. But there's another narrative in which analysts suggest that the energy efficiency gains made by the IT industry, its adoption of renewable energy, and the emission savings that IT can bring to other sectors of the economy could in fact bend the climate curve. And there is ample evidence that historical IT efficiency gains have been remarkable. For example, a recent study by Lawrence Berkeley Lab points to a near plateau in US data center energy use in the past decade, despite massive growth in data demand over the same time period. And this plateau is attributable to large efficiency gains in servers, storage devices, and network equipment in data centers. So in today's panel, we're going to explore where digitalization may be headed from multiple perspectives. We'll talk about processor design and fabrication, the digital systems that they enable, and some emerging applications of these systems, such as artificial intelligence. And we'll discuss ways that IT can maximize its potential for bending the climate curve. So my first question goes to Rob. As we saw in the data center example, processors have seen tremendous efficiency gains throughout their history, which has enabled massive growth in computing with comparatively pretty small growth in energy use. But one of the most common concerns moving forward is that Moore's law is slowing down. This means that future efficiency gains might not be enough to offset future demand growth, and that could lead to sharp rise in energy use and emissions globally. So my question to you is, how much bandwidth remains for improving processor efficiency moving forward, and what innovations are being pursued on this front by the semiconductor industry?
All right, thanks, Eric. That's an excellent question. If you look historically at pretty much any processor that's been out there, it has a power envelope or an energy envelope that it needs to operate in. And that's true for anything from a massive data center out of servers down to the smallest microcontroller-based object that you would attach to a wall and forget about. And because of that, energy bound essentially on computing, computer designers try to figure out how they can get more processing power into the same energy envelope. And that's really, I think, why the plateau that you mentioned has existed. The way that ARM has always advocated doing that is to treat the entire compute problem as a system, ranging from the device level all the way up through the application software, and to kind of co-optimize all those pieces. And when you do that, then you're able to achieve the kinds of power reductions that we're talking about. A big chunk of that historically has been via Moore's law. So, we're used to every generation, the power gets a little bit better per device, which means you can pack more devices into the same power envelope. And that, as you mentioned, has been slowing down. Now, I've heard predictions for a long time that it's going to stop, and all those predictions so far have been wrong, but eventually one of them will be right. So whether there's a 2x improvement in devices or a 10x improvement in devices, I think we can be pretty sure that there's not anymore an infinite runway of such improvements. And that means that you have to approach the problem differently. Typically, what's been done up to this point has been primarily through better algorithms, better optimized microarchitectures, and so on. What we're thinking, though, is going to be a real boon over the next 5 to 10 years is going to be moving to more 3D-based solutions. And by that, I mean die stacking type solutions, the way we currently see in NAND flash, for example, or the way that we've seen in systems where there are high bandwidth memory stacks and this kind of thing. And we think those are going to move on into first the infrastructure domain, where you'll see high performance processing coupled to very localized memory. And the vertical stacking essentially allows you to get more connectivity bandwidth, and it allows you to get that bandwidth at lower capacitance for lower power use and also a lower delay, which means improved performance. So the 3D aspect of Moore's law has not yet begun really in earnest, but when it does, I think we'll start to see some very, very serious gains in performance, and that those have a runway of die stacking just in conventional techniques with through silicon vias and so on. And they also have a roadmap ahead in monolithic die stacking, but that's a few years out there, where you can actually stack multiple layers of logic and memory. And there have been academic examples of this already, where people have stacked nanotubes and things on top of regular logic devices. But I think we'll start to see more interesting forms of that and more commercially viable forms of that going forward.
Got it. Thanks, Rob. So die stacking could be another path forward to sort of circumvent perhaps the slowing down of Moore's law in the near term through better chip design. So following on that, I'd like to ask Ellie a question from Applied Materials. So, we just heard from Rob that there are some innovative new ways of designing and fabricating processors. And I understand from you that there could potentially be significant bandwidth within the chip fabrication process itself for improving energy efficiencies. Could you tell us a little bit more about how that works and what's happening in the semiconductor fabrication industry in this regard?
Sure. Thank you, Eric. And thank you, Rob. So when we see that, imagine a world of trillion devices connected together, we project our industry is going to be much bigger. And for semiconductor equipment, it's going to reach about $100 billion new equipment every year. So there are really three things that we have been focusing on and need to continue to focus on. One is to continue to design and make semiconductor fabrication equipment much more sustainable. Secondly, we need to continue to drive the silicon processing to continue to improve the PPAC performance. So everybody knows PPAC stands for power, performance, area, and cost. And finally, we continue to work with our customer to innovate new materials and chip architectures. And, I'm going to talk a little bit about that. So from manufacturing equipment, we have this design for sustainability called 30-30-30. 30% power reduction or electricity reduction by 2030, and also 30% of chemical consumption reduction by 2030. There are many different ways to reduce energy, sharing components, for example, pump, the heat exchanger, and so on, and also design lower, better energy efficient generators, and also use sensors to have equipment go into idle mode so they're not in use. We also have a roadmap to continue to design the configuration of our platform and also chambers to reduce the footprint, reduce the chemical consumptions, so that we can eliminate emissions and eliminate energies. So that's from the manufacturing standpoint. From silicon processing standpoint, driving PPAC, we are growing a suite of integrated material solutions, which means that we bring chambers together under pristine vacuum conditions so that we can optimize our circuit performance to drive lower leakage. For example, for the gate leakage, we have been able to improve orders of magnitude, and that translates directly into the battery life for the edge devices. Another good example for PPAC improvement is a new product that we're launching this year at Semicon West. It's called selective tungsten. Tungsten is not a new material, but this is a new innovation where we don't need to have a barrier liner going down. So you have increased volume for this low resistance tungsten to fill, and that eliminate about 40% voltage drop across a very critical bottleneck between transistor and interconnect. So we continue to work with our customer to continue to drive PPAC performance, and this selected tungsten is going to enable for us to scale beyond 5 nanometer. Finally, in terms of compute architecture, Rob talked about stacking. Right now, the compute architecture is actually not very energy efficient. The SRAM and DRAM actually consumes a lot of power because you need to continue to supply energy so that it can keep its states. There's a new emerging memory that we're working on is called MRAM. It's a magnetic material. It's non-volatile, which means that when the power goes off, it actually keeps its state. MRAM is not an easy technology to integrate, and industry and we have contributed to making it work, and it's being adopted rapidly because it's demonstrated that it can save the standby power by about 10x. And another thing about MRAM is that it has a very rich roadmap. So will people continue to work on scaling the speed, continue to work on scaling its power. So there's a device on the horizon called VCMA. It's a voltage-driven MRAM. And if the industry are able to make it work, you can reduce the active power by about 10x. So we're very excited about the compute architecture working on, the circuit that we're working on, and also the equipment energy saving that we're working on, and continue to try to bend this climate curve.
Oh, thanks, Ellie. So it sounds like there is bandwidth to reduce the energy use in the fabrication process itself, but also through the introduction of new materials, new designs, and so forth, you can continue to improve the efficiency of the circuits, the products themselves. I'm wondering if anyone in the panel from the client side could talk a little bit about how these new chip materials and technologies could be adopted. Is there a problem there? Is there perceived risk with adopting new technologies like this?
I'm happy to jump in. I think there are both problems and risks and opportunities with the new technologies. I'm from Google, and as people may know, we've been building some of our own chips for neural network applications over the last 7 years or so. As part of building them, I think we've been willing to break previous abstractions. We're not necessarily building general purpose CPUs or GPUs. We're building new kinds of computers to serve our application needs, which right now are huge in the neural network and deep learning space. And as part of breaking previous abstractions, we've changed mathematics, we've changed our networks, we've changed the number of cores per chip, and many other things which previously might have been set in stone. So I think we're willing to break abstractions at all levels of the stack. And so speaking to what Ellie was just talking about, if there are things that are not quite perfectly traditional transistors or not quite SRAMs, but had other capabilities or ways that they could efficiently do calculations that met our application needs, we'd be really interested in those. And those might be enablers for the next 10x step in the 6 generations from now TPU, which could go incredibly aggressive with something like an analog computation technology, or with some sort of die stacking memory, or even back end of line integrated memories on top of the compute layers of the chip. I think we're open to those possibilities. The thing is that Google is first a software company and a search company, and so we're not super deep in the materials side. Maybe we're only just barely into the architecture business. And so we need partners that can teach us about what those trade-offs are to explore that space together. I think we can say things about our application requirements that might change what's important about the devices that we'd like to put into our chips and systems.
Got it. And creating that market is super important for the semiconductor fabrication as well. So it's nice to hear about these potential emerging partnerships. I'd like to move on to Samantha from Intel. Now, Intel has clearly made major contributions to improve processor efficiencies over the years, but I'd like to zoom out a bit and focus on one important destination for all of that computational power, which is data centers. So data centers currently account for 1% to 2% of global electricity use, and there's mounting concern that their energy use will rise in a world where we have many more billions of connected devices and a massive increase in the data demand from those devices. So we've just heard from Rob and Ellie, and also Cliff, that future energy efficiency improvements may help mitigate some of this energy use. But you're seeing potential for cloud data centers to play another important role in climate change mitigation, namely as a resource for renewable energy. Can you tell us a little bit more about how that might work?
Yeah, absolutely. Thank you so much. So, as you said, global data centers are amounting for 1 to 2% of energy use today. But I've seen some really pessimistic numbers that put that at 30% in 2030. Now, that's like a really scary number, right? Assuming that energy consumption is actually carbon based, right? But if it's renewable, it's all right, right? So, we heard, Ellie and Cliff talking about opportunities for collaboration here. And I really think that collaboration is the key to making making the data center here as efficient and as green as possible, right? Because we all have our areas of expertise and we all need to come together to solve this problem. But what problem are we actually solving here, right? It's really, we want our data centers to be carbon free, ideally, right? But if we can get to carbon neutral, that would be awesome, right? But it's not just like the data center, it's the power that the data center is getting, right? And that is reliant on the power grid. And the power grid has to be stable at all times, right? Which means that there's an equal amount of supply and demand. But natural resources aren't just available when we want to stream our videos, right? So we need something to be able to consume that energy when it becomes available, when the sun is up, when the wind is blowing, something like that. And so data centers are in a really unique position to be able to consume that energy. And that's because of the types of workloads that we run, right? We have some like really high compute, high energy consuming workloads like AI training or HPC that don't necessarily need to be completed at the drop of a dime or at any specific moment. They are just executing, right? So if we were able to run these workloads when we had this excess of green, clean energy, right, now we have these really high compute workloads running clean, right, which is exactly what we want, right? So, but what if we take this a step further and we only had the data center running when this clean energy was available, right? So we have a data center that's awake when we have this excess amount of green, clean energy, and then asleep when it's not. And this actually leads to quite a few different cool new design paradigms that we can really address as a community. First is if we're running clean and we're running as much and as fast as possible, it's going to get real hot in there. So cooling infrastructure is really important. But if we're spinning up a data center at within minutes, traditional cooling mechanisms aren't going to work. So we need to do and look into more research like liquid cooling, things along those lines. But we also have to ensure that the liquid that we're using is sustainable. But there are other cooling mechanisms, right, that need to be explored. But also, if we're assuming that we're running in a liquid cooled environment, we also can design better chips with higher TDP, with higher frequencies. So cooler stuff, which is what we all really want. The second is what happens when we run out of those renewables, right? When we need to go into this sleep mode, we need to be able to save our state, which is something that Ellie was talking about earlier, which is a persistent memory, non-volatile memory. We want to be able to save the state, load it back up, and continue executing when the energy becomes available again. And finally, we need software to control it all, right? We need software to be able to wake up the data center. We need software that will pack as many workloads into that server as possible, and then tear it down, put it to sleep. So, besides just, those three things I mentioned, there's tons of opportunities here. And what's great is that it's running clean, right? Which is a benefit to everyone, right? And as a side effect, we're also stabilizing the grid, which means we could put more green energy on that grid instead of relying on carbon, right? So at the end of the day, I talk about materials, hardware, and software. And, it takes everyone's expertise to be able to make this a really green, wonderful environment and develop some cool tech.
Mm-hmm. That's really exciting to hear. Now, just a quick follow-up question. So is this happening already, even on a small scale? And if not, how soon do you think it could happen?
So yeah, actually, it's starting now. So Google has put out a blog recently where they have started looking at being able to use green energy in some of their data centers. It's a concept called time shifting, where they're able to deploy some of their workloads when this energy is available. So it's starting, right? But we also have a lot of features within the components, and each little component within the data center that needs to be taken advantage of. And so hopefully we can all come together and showcase this as a shining example of something that we can do.
You mentioned something else that I'd like to follow up on. When you said earlier that it may be that data centers' energy use grows globally, and as long as that's running on renewable energy, that's okay. It struck me that, there's been a lot of work looking at the benefits of IT systems and data centers elsewhere in the economy. And there's an argument that if data center energy use goes up and it's powered by renewables, that's okay because we may get greater savings elsewhere in the economy. And I wonder if anyone else in the panel has thought about this and would like to chime in on that important point.
Sure, I can take that, Eric. If you think about the days before the internet, we used to drive to the bank, we used to drive to the store to buy things. And now we do that online. And you think about the amount of energy saved and even dematerialization of buying music online and watching movies online. And that's been expanded significantly with this new innovations, IT innovations such as AI and machine learning, edge computing, IoT. Those are enabling even significantly further dematerialization and energy reduction across industries, including renewable energy, being able to integrate more renewable energy into the grid with smart devices, with electric vehicles. Think about smart cities, smart manufacturing. That's all being enabled by these IT technologies, which will have huge impacts, not only on decarbonization, but other sustainability benefit outcomes.
Really great points. And I can say, coming from the analyst community myself, that we need a lot more life cycle assessment oriented studies to try to tease out these net benefits. And they can be really complex. I mean, this could be a topic for a whole other panel discussion some other day. But Nicola, I'd like to stick with you to follow up on this thread a bit more. So you just raised a really good point about the need to consider these broader benefits. And a lot of studies suggest that these could be substantial. Regarding your role at VMware, we just heard from Samantha that there could be overcapacity in cloud, on-premise, or other types of data centers that could be harnessed for renewables integration. However, there are other examples of underutilized IT resources that are in fact wasted resources, right? Virtualization has already reaped pretty large energy savings by improving capacity utilization while also reducing e-waste. So tell us a little bit more about virtualization. How important will it be in the future for minimizing impacts? And what are the types and magnitudes of wasted IT resources and what can be done about it?
Sure, absolutely. So before I actually step into virtualization, I want to take a step back and talk about the use of energy at a systems level and the energy losses that we have for computing. So if you think about in the computing world, you start with the energy that's produced at the power plant and then is delivered to the data center, then to the servers, and then results in productive computing. But there's a lot of losses along that chain, significant losses at the power plant and transmission, and then in the data center for cooling and power supply, and then even in the server itself with fans for cooling the power supply, and then of course underutilization of the server itself. So at the end of the day, we start with 100 watts at the fuel side, and we end up with about 5 watts being used for actual useful computing. So the real opportunity here for improvement is actually at the useful computing layer. Because if we can double that in the physical server, double the useful computing, we can have the amount of energy that's required for that computing than we have today. So virtualization is a perfect example of how we've, in addition to the hardware efficiencies that we've seen, virtualization of the software layer is a perfect example of how we've been able to significantly increase that useful computing. So before VMware, enterprises would deploy applications like databases or email on each application would go on its own physical server, because if you put more than one application on a physical server, you would have performance issues. And I think we've all experienced this on our own computers when the virus software is running and everything slows down, or if we have too many web browsers open, there's not enough memory, right? Everything just slows down, but enterprises don't want that, so they would run one application on a physical server. That would result in significant underutilization, usually about 5 to 15% only of the physical server. Then VMware came along and cracked the x86 architecture in a way that allowed the applications to be orchestrated to access the CPU, memory, and I/O of the machine. And that was really the VMware hypervisor layer. And so as a result, enterprises now could run many, many, many applications. So instead of having 100 servers for 100 applications, they could have maybe 10 physical servers for those 100 applications. And you could imagine the impact that's had on compute efficiency and decarbonization. In fact, VMware had commissioned IDC to quantify that impact, and they found that in the cumulative, since the beginning of virtualization to 2018, we've avoided about 130 million physical machines being deployed, 2.1 million gigawatt hours of energy saved, and 1.1 billion metric tons of carbon emissions avoided in the atmosphere. And if you think about that in terms of global carbon emissions, that cumulative avoidance was about 3% of 2018's global carbon emissions. Now let's talk about some of the opportunity we have to further improve that productive compute capacity in the form of what exists today, which is stranded compute capacity. This is in the form of things like zombies, where these servers, physical machines, or virtual servers were deployed at one point for a useful purpose, and then they were left. The project ended, the person left the company, and now those machines aren't being used at all. But they're still powered on, still churning out carbon. And that's a huge cost to a company. It has security vulnerabilities. It's very much a human problem, but it can be solved technologically. And it represents maybe 20 to 50% of compute capacity out there. It's an enormous problem. We have things like a siloed spare capacity, where organizations have siloed computing and they can't share across that, even though they may have spare capacity that each other can be using. And then there's oversized virtual machines where they're reserving more CPU memory than they actually need. And then you have times where that capacity maybe isn't being used overnight and actually could be turned off as a last resort if that spare capacity can't be used. So this stranded capacity is very expensive for organizations, and there's a huge opportunity on the technology side to solve this problem, which would have further, as you could see, energy and carbon reduction benefits.
So it sounds like this approach will be even more important moving forward as we're looking at connecting more people in the world to devices, increasing data, rise in application use, and so forth. And it's exciting to hear that there are still possibilities left. I do know from the LBNL study, looking back to that study, virtualization explained a lot of the energy savings that contributed to that plateau in the United States. So really interesting stuff. Cliff, I'd like to turn it over to you now, because as we've heard, virtualization is an application that has clearly been an environmental and sustainability success story for the IT industry. But I want to shift gears to another application, which is probably the most talked about, most hyped application these days, which is artificial intelligence. And the sustainability implications of AI are still pretty fuzzy at the moment. We know that AI is still in its infancy, but we also know that AI can be very computationally intensive. Some early analyses have projected that AI could lead to explosive growth in energy use over the next decade, although I suspect that maybe those studies haven't fully considered the potential for improving algorithmic or computational efficiency. So maybe you could tell us a little bit more about the role of AI in sustainability, how you see it, and what do you see as the prospects for improving the efficiency of AI moving forward, so we avoid this explosive demand growth that some are predicting?
I think we've seen a sequence of really great breakthroughs from AI in recent years in a number of different fields, in vision, in speech understanding, in translation, in playing games, and solving complex control problems, and doing robotics. And all of that's been fueled by exponential increases in computation. We're doing huge matrix multiplications on models with ever-growing numbers of weights. And in fact, the competition to achieve higher and higher accuracy looks like a space race. Like different labs across different parts of the country keep on building bigger and bigger models. There's a space race in the language understanding task in particular. If you look at BERT models and GPT-2 and 3 sorts of models that are being deployed, they each get better and better at accuracy, and they do that at an exponentially increasing cost. I think the curve is something like doubling every 15 months, which is faster than Moore's law ever was. So that's maybe the worrisome side of things. On the positive side of things, there's also a recent blog post from OpenAI pointing out that the efficiency in doing our training for neural network models has gotten better as well. That in the 8 years since AlexNet debuted, we're now able to train a model to that level of accuracy something like 50 times more efficiently. than then. So methods have also improved in accuracy. We don't tell that story as much. And I don't even know like whether the factors cancel each other out. Part of the way to getting to the giant new models is that you have to find more efficient ways of getting to them. But it's not that all hope is lost. I think it's that there's this huge revolution going on, and some of the initial ways to first get to a result are less efficient because we haven't had the time to clean things up, to figure out what the best way to do things is. To make a historical analogy, it feels kind of like the Industrial Revolution, where the early steam engines were incredibly clunky and were terribly inefficient from a conversion of burnt fuel into effective work perspective. Nowadays, we have thermodynamics, and we understand how to do much better engineering and much more efficient translation from fuel into useful work. And I think AI is kind of at that stage, that we haven't really figured out the most cost-effective way to train or the most cost-effective way to serve or infer. But I think those breakthroughs are coming along as well. Like if you look at our original TPU, it looks like it's on the order of 30 times more energy efficient than the CPUs and GPUs that were its contemporaries. And we keep on innovating on the hardware front. If you look at what people are doing in phones are by necessity power constrained. There's only so big a battery, and you don't want the thing to burn a hole in your pocket. And yet we have voice recognition on our phones, and we have smart image processing on our phones these days. And so I think that the engineering is going on to make AI sustainable. I think the sort of space racy kinds of things are worrisome if they get widely deployed, but I think that economics will get us to strike the right balance between, first of all, doing the science to show what is possible, and then once we've figured out with the limits of effective science what is possible, we can then back that off to, okay, having known this is as good as you can do, now how do we change that to be cost effective and mass produced in a way that doesn't literally boil the oceans? So I think that is insight. I don't think you'll see as much in the neural network researcher literature about efficiency, because they're still going after accuracy by using whatever means they can. As the accuracy things mature, as we figure out what the capabilities are, there will be a second race to do it efficiently and commercially. And I think that that will all be to the good. So I'm maybe a little less worried about boiling the oceans. I think the potential is there, but I think that we still live on one planet. We still have to pay for all of these experiments. And so those constraints will come into play and make sure that things stay sane.
Yeah. And so one message I'm hearing is that we shouldn't draw, conclusions based on the early days of AI, because there's a lot of innovation that lies ahead and a lot of, frankly, economic and other forces that should drive continued efficiency. Rob, you've had some thoughts about, how can we set up AI problems to be a bit more efficient?
Yeah, exactly. I was thinking about that with Cliff's response. There's examples of constrained systems, particularly edge systems, automotive systems, and so on, where there's a fixed compute power or compute energy envelope. And rather than achieving the best possible accuracy under any circumstance, you can actually tailor the system so that it achieves as good accuracy as you can, given the power requirement that you have. And so the phone example was a good one. There's now dedicated neural processors on phones. We're starting to see the same thing in microcontroller-based systems as well, where somebody will use an Ethos NPU or something as a companion to the microcontroller that's already there. And then, as Nicola was mentioning, you have this sort of distribution of things that are on and things that are off. So you can have the maximum power envelope constrained by the battery or by the heat dissipation, but you can have the processing power at any given moment dedicated to an NPU or to a microcontroller or to whatever else you have. So I think a lot of the efficiency gains that we'll see going forwards are going to be due to the addition of custom processing units within a fixed processor volume, physically, I guess.
Okay, so I'm going to go over to Mo now, because I know, Mo, you also work with artificial intelligence. And my question to you now relates to another trend I'm hearing about, which is the proliferation of edge data centers in the big data era, facilitating the Internet of Things and their implications for energy and climate change. And some of this could even be, local AI type computing. I've seen some studies that imply that edge data centers may soon lead to large growth in energy use, because it's kind of like a reverse migration in some respects, back away from the cloud to smaller and less efficient local data centers. But I think you may have a different view on this, what the opportunity space looks like for edge computing. So can you tell us, are there ways to maintain or exceed the energy efficiency we're seeing in the best run cloud data centers if we move to the edge?
Yeah, this is a different angle and an interesting one. I share the same sentiment with Cliff and Rob, that here we have really two views on how we're going to move forward. One school of thought, as you mentioned, paints a gloom and gloom day of burning our planet dry. And the other one is, hey, no, we're going to basically get a hold of it and make sure that this is going the right direction. I happen to subscribe to the latter, and based on what we've seen what AI can do, especially when it comes to the edge. AI is a foundational technology. Andrew Ng calls it and compares it to electricity. AI is the new electricity, and as a foundational technology, it can power good and it can power not good. On the good side, we have a lot of potential to move forward, especially when we bring AI to the edge. Why edge is important? There are lots of AI-driven tasks and benefits that we derive from AI that they're local. They're local in nature. You want to know how many people are in a room, people counting. This is very valuable because then the whole HVAC system of the whole building can be more efficient. You can significantly lower the balance of energy consumption in major buildings. But there are two ways to do it. You can basically stream the camera to the cloud and do all that. And first of all, the act of transmitting data, the network cost is significant, especially it happens over radio and mobile networks. And then once it gets there, you have a lot more bigger machinery to process that. You can do people counting on the edge with a QVGA sensor at milliwatts. And the number and the metadata can be used for all of those efficiencies. Or you can send the data and put it back in the data center in the cloud, which can cost probably watts. So we're seeing like orders of magnitude here of difference. That's one thing. The other thing that I think Nicola touched on was doing renewable energy at the edge is sometimes there are opportunities that makes it easier. Wind and solar, there's like free cooling. You can, if cooling is a major energy cost for a data center. It's about 40% of the energy cost of the data center. And if you use heat sinks, if you use smaller specialized processors to drive the inferencing on the neural network that you're doing, I don't know, whatever you're doing with the edge AI, then all of a sudden you get this benefit from solar, from free cooling, from wind, and then you can add that the real-time assessment of supply and demand. So overall, you can achieve a better energy consumption balance.
And Eric, one other point on that is that just like I was talking about the spare capacity, sort of siloed spare capacity, is that most of these edge computing systems won't be utilized fully, right, all the time. And so there's going to be spare capacity. And if we can find a way to access that and use it for other computing, then it's almost like you have a virtual data center, right, that's just distributed. So long as we're maximizing the use of that compute, then it doesn't matter where it is, right, how distributed it is.
Yeah, that makes a lot of sense. Thanks, Nicola. What I'm hearing is the move to the edge doesn't necessarily have to mean a rise in energy use, because of some of the technological strategies Mo mentioned, the resource efficiency strategies that Nicola mentioned, and others. But it sounds like it's definitely an area that needs some more study and some diligence with respect to how energy is managed and what technologies go into the edge, because it will be an important part of the solution. So we're getting toward the end of our panel session. So thank you, Mo, for those comments. Thank you, Nicola. If I had to recap what I've been hearing today about IT and climate change, I think really the one phrase that immediately springs to mind is it's complicated, right? On the one hand, there's clearly no end in sight for growing demand for data and computations as the world becomes increasingly interconnected. So there is a risk that we'll see a rise in energy use and potentially a rise in greenhouse gas emissions if we can't continue to improve efficiency so that we outpace those demand gains. On the other hand, this panel has described a number of critical innovations that are occurring both within the IT industry and across some of the key IT applications like artificial intelligence, which suggests that there really could be significant potential for IT to bend the climate curve. But what seems clear is that these innovations are not going to arise without massive efforts by the IT industry and really large-scale commitments to addressing climate change, including by the semiconductor industry. So I'd like to pose one final quick question to all members of the panel in 1 minute or less. Brevity is key here. What do you see as the most important action item or items that the semiconductor industry should pursue in the next decade to enable us to bend the climate curve? Let's start with Rob.
I guess what I would look to improve our energy efficiency globally in the future would be to improve our memory systems. So moving data around is incredibly inefficient, and bringing the compute closer to the memory is, I think, the path forward, whether that's through die stacking, as I mentioned earlier, or whether it's through moving AI to the edge, or whether it's through improved memory structures, such as the MRAM that LA was mentioning earlier. Each of these things, I think, has something to contribute. And this will require re-architecting our systems a little bit. Persistent memory is different than non-persistent memory. There are security implications to where data is and how it's accessed and so on. But this is definitely a field where there's a large amount of untapped gain, essentially. We are, in some sense, the early steam engine phase, as Cliff was mentioning. So I think there's a lot of improvement in memory systems that's available, and I look forward to ARM participating in that and the other panelist companies as well.
Okay, thanks. Nicola, your thoughts?
I would say the hardware-software interface in making the hardware provide more information to the software layer about the productive utilization of the hardware itself. So saying, hey, my memory and CPU aren't being used productively, and maybe tying some costs to that or as a motivator. That would be my recommendation.
Okay. Cliff, over to you.
Yeah, quick +1 to what Rob said about memory systems. Moving the data around is one of our most expensive things. And even moving things over cellular networks is expensive. In addition to that, if I could wave a magic wand, I wish we had a return to Dennard scaling. I don't know whether there are technologies around that have that virtuous property to it where the devices keep getting better every year for the same power cost, but that would be ideal if anything like that could be found.
Okay. Mo, what are your thoughts?
Sure. So I think if we get ourselves into trouble, we've done it by creating a mess by 1,000 cuts, borrowing from Taylor Swift. And the way out of it is going to be by 1,000 small little acts of lifelines that we get through efficiencies on various. So it needs to be an intentional, organic efforts coordinated by us as the industry, government, and individuals. From this semi-industry, something that I think it will make a huge difference is, and the industry is going that way. I'm hoping that I invite all of you, to accelerate it, to lower special purpose chips that are meant for edge AI acceleration, things around sub 100 milliwatts. That will have a major impact on our energy consumption.
Got it. Samantha, what do you think?
Yeah, so I actually am going to add on to what Nicholas said, because I totally agree. There needs to be a much better collaboration between, manufacturing hardware and software. And this is where we're going to gain probably, I think, the most efficiencies, especially in the data center. We all have our expertises, and we're all going to continue to drive innovation in our respective areas. But we need to make sure that all of them are connected together much better than they currently are today. And, not just that, I think from just our individual companies' perspective, like what are each of the things that we're doing that are driving towards a more sustainable future? From the manufacturing side at Intel, I think we've pledged by 2030 to be 100% green, zero waste in our global manufacturing, and then have net positive water usage. I mean, so every company needs to be doing something similar, right, to be able to drive at an individual level, plus add in extra better design features within our products and how our products are being used, right, whether that's designing in better power management features. But also the other important thing is that everyone needs to be able to use these features, right? So contributing to open source, like open source projects, like it really doesn't make sense for any one company to be able to leverage these features. It really only makes sense if everyone's doing it. And so consortiums, standardization bodies, open source software to be able to take advantage of everything is really key, because we all need to be making the world a better place.
Yes, would wholeheartedly agree. Okay, last but not least, Ellie, what do you think?
So as an equipment and materials engineering company, we're going to continue to work with our customers to drive PPAC scaling and PPAC Moore's law, if you want to say it that way. And whether or not it's new memory packaging, we talked about, moving data and even photonics. But I think that, through this discussion, it's very clear that it's a small piece of the puzzle. I think we're all independent. So we need to drive co-optimization, within this ecosystem. We call it the material systems or system to materials. And, I heard about several panelists talk about the interesting looking at packaging and new memory and so on. We have lab here in Santa Clara and lab in Asia as well, where we link our product together. We call it the integrated module, integrated material solutions. So we open this opportunity to, to the panelists, the companies here, to get it to work with us. And just to quote Cliff's AI forum message last year, I think he talked about, let's push Google and AI company down closer to device and materials, and then push the materials device people, back up. So I think that's something that we should do to continue to drive the industry forward. So thanks, Eric, and then thanks to the panelists. I learned a lot from all of you. So thank you very much.
Yeah, I certainly did too. And, this is just the beginning, hopefully, of many conversations on this topic. I think we were able to really cover some interesting ground. I certainly learned a lot. So thanks to each of you for joining me, and thanks to Applied Materials for organizing the panel, and to the virtual audience out there. I hope you've enjoyed it. Hope you've learned as much as I did, and hope you enjoy the rest of Virtual SemiCon West. Goodbye.